In this video, we'll talk about the LP formulations in general form, and we'll discuss the implicit assumptions made by any LP models. For this purpose, we will look at the following working example. So this is a production planning problem. We assume that we have a manufacturing facility that produces n products given by P1 through Pn, and it uses m different types of resources, such as raw material, labor, it could be money, and other things. So these resources are denoted by R1 through Rm. We know that each unit of product Pj sells for Cj dollars. And we also have the constraints on resources. So we assume that the resources are already there. We already purchased them before. So this is what we call the sunk cost. We already paid for the resources and now we need to use them in the most efficient possible way. So the amount of resources available would be Bi units for resource Ri. And this is for I between 1 and m. Producing 1 unit of product Pj requires Aij units of the resource I, and we need to decide how many units of each product we want to produce so that we maximize the total revenue. This is a very typical situation, and in fact many examples that we considered so far fall within this general framework. So we know very well how to formulate this type of a problem. We use index I for the resources and j for the products, and then our decision variables would be xj, which is the number of units of product j to produce. Then the objective is easy to formulate. Specifically, our objective is to maximize the total revenue, and the revenue that we get from the product j is given by Cj xj, and then we sum up the contributions of each product to the revenue to obtain the total revenue. And of course, we are maximizing, so our objective is to maximize the summation of Cj's xj's over j between 1 and n. Then the resource constraints just express the fact that the quantity of each resource Ri is limited, and the limit is given by Bi. To express the total amount of the resource I that we use, we need to look at how much of the resource I each product J takes. And that is given by Aij. So therefore, if we produce xj units of product j, the total amount of resource I used by the product j is given by Aij times xj. And again, we need to sum this over all the products between 1 and n in order to get the total amount of the resource I used to produce all the n products. And this total cannot exceed the upper bound on the resource given by Bi. And all of this is done for every I between 1 and m. And finally, we have the non-negativity constraints expressing the fact that we cannot produce a negative quantity of a product. In summary, we obtain the following formulation. We maximize the revenue given by the summation of the revenues obtained from the individual products, subject to the m resource constraints, and then we also have the non-negativity xj is greater than or equal to 0 for all j between 1 and n. This is a very standard LP formulation, and we can write it out in an expanded form as shown on the next slide. So if we spell out all the summations that we have in our formulation, then the objective is to maximize C1x1 plus C2x2 plus C3x3 and so on up to Cnxn. And then the first resource constraint has the total resource that we use to manufacture all the n products given by A11x1 plus A12x2 and so on plus A1nxn, and this is less than or equal to the limit that we have on the resource 1, which is given by B1, and we write a similar constraint for every resource. So these are our M resource constraints. And I want to emphasize that in this formulation, Cj's and Aij's are the fixed parameters. These are the data that are provided, and then Xj's are the decision variables. All of this can be written in a much more compact format if we use the matrix representation for our data. In fact, all the coefficients from the objective can be put in a single vector. Then all the right-hand sides of the resource constraints can be put in another vector. So the vector for Cj's will be of length n. The vector for Bi's will be of length m. And then we can put all the coefficients that we have in the left-hand side of the constraints into a single matrix with m rows and n columns. First, before we do that, let's formally discuss what a vector and a matrix are.
Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
A real n-dimensional vector is just an ordered set of n real numbers, x1 through xn, and we usually write it in the form of a column, x1 through xn, and we say that it belongs to Rn, which is the n-dimensional Euclidean vector space. Also, we could specify all of these entries of the vector in a row. In this case, it would be a row vector. So, but by default, for clarity, we assume that whenever we talk about a vector, we talk about a column vector. And then we transpose that column vector in order to obtain its row version. We can also represent this vector in a compact way by writing x is equal to xi's for I between 1 and n. So essentially this is the vector of length n with entries given by xi's. Now what about a matrix?
The matrix is a system, Neil.
An m times n real matrix is a rectangular array of real numbers consisting of m rows and n columns. So usually when we say that we have an m times n matrix, this means that there are m rows and n columns. So rows go first. We already mentioned the transpose for a vector. So when we transpose a column vector, we essentially obtain the row version of the same vector. In a more general case of a matrix, if we want to transpose a matrix, we essentially write all the rows of the original matrix as columns of a new matrix, or the other way around. So essentially we swap rows and columns, and this way we obtain the transpose of a matrix. If our original matrix was m by n, then the transpose matrix is going to be n by m. Now we are ready to put our general LP formulation in the matrix form. Recall that when we were discussing this generic production planning problem, we had the objective of maximizing the summation of Cj's xj's for j between 1 and n, and we had the m resource constraints that we spelled out this way right here, and of course we also had the non-negativity constraints for all the variables. Next, what we're gonna do, we'll put the coefficients used in this model into vectors and the matrix. So for the coefficients in the objective, we'll represent them in a vector C of length n. So it's gonna consist of C1, C2, and so on, Cn. And remember that we agreed that by default our vectors are column vectors, therefore since we wrote it in a row, we will put the transpose sign here to indicate that C is a column vector. Then the vector of variables x is given by x1 through xn transposed. Similarly, the vector b will be the vector of right-hand sides. So you'll have b1, b2, and so on to bm. So this vector is of length m, and we explicitly write it as a column vector, so I don't need to put the transpose sign. And finally, we will put all the coefficients used in the left-hand side of the constraints into an m times n matrix. So you see we have here m rows and n columns, and we'll put all of these coefficients in the matrix A, which is given by A11 through A1n in the first row, then A21 through A2n in the second row, and so on. We have m rows. The last row is going to be AM1 through AMN. So this is the matrix of the left-hand sides of the constraints. And usually we call this the technological matrix because essentially this matrix, these coefficients here, describe the technology by which we produce the products, all the requirements of the resources, and so on. So how do we represent things now in a compact fashion using these notations? So let's look at the objective first. Here we have C1x1 plus C2x2 plus C3x3 and so on plus Cnxn. And looking at how we define the vectors c and x, this is nothing else but the scalar product of these two vectors, c transposed times x. And recall that the scalar product is exactly the expression that we have here. So you just have the component-wise products of the corresponding entries of the vectors, and then you sum up those component-wise products. So the left-hand side of these constraints here, if you want to put them in the matrix form, then this is nothing else but the product of A and the vector x. If you multiply two matrices, then the ijth entry of the resulting product matrix is given by the scalar product of the ith row of the first matrix by the jth column of the second matrix. So essentially you multiply every row of the first matrix by every column of the second matrix, and of course you need to make sure that the length of the row of the first matrix is the same as the length of the column of the second matrix, meaning that the number of columns of the first matrix in the product equals the number of rows in the second. And in case of a matrix by a vector, the way we treat vector is it's a matrix consisting of n rows and one column. All right, so and because the matrix A has n columns here, when we multiply the matrix A by the vector x, what we'll have as a result, the first entry of the product is going to be the scalar product of the first row of A by x, which is just a column vector, and it will be exactly this expression right here. Similarly, the second entry of the product will be the second row of A multiplied by x, which will give us this here, and so on. Ax essentially gives us the vector of all the left-hand sides of the constraints here. And finally, the right-hand side vector is given by b. And as a result, we can represent all the constraints by just saying Ax is less than or equal to b. So therefore, in summary, we have the following very compact representation of our LP. We say maximize C transposed X subject to ax is less than or equal to b and x is greater than or equal to 0. This is a standard matrix representation of our general LP, and we can put pretty much any LP in this form. Okay, by now we have considered many different linear programming models arising in various situations, and we have seen that we can solve some small-scale cases easily in the solver, but in fact, software based on the state-of-the-art algorithms for LP is very scalable and can handle problems with millions of variables and constraints. And this scalability of the state-of-the-art algorithms for LP is what makes it one of the most attractive optimization-based tools in real world. All right, the relative simplicity of these models as well as the powerful tools we have to solve them are two main advantages for LP. But like any technology, no matter how powerful, linear programming has its disadvantages as well. And in fact, the simplicity of LP models, which we stated as one of the advantages, happens to be is also the main disadvantage of linear programming, because in many cases linear models are overly simplistic. The linearity assumption is very restrictive, and most of the real-world processes are nonlinear by their nature. So therefore, the question arises, how adequate are the LP models in describing these real-life processes? So let's discuss in more detail the implicit assumptions that come from using the linear models. All right, the implicit assumptions that we make in any LP model are listed here. The first two of these assumptions are essentially a definition of a linear function. To illustrate, consider a simple example, let's say 5x1 plus 3x2. Obviously, this is a linear function having just two variables, and the proportionality assumption says that the contribution of a variable is proportional to its value. And of course, this is the case for linear functions because the way the variable is included in the function is with the coefficient. x1 is included with the coefficient of 5, x2 is included with the coefficient of 3, and the contribution of each variable towards the function value is proportional to the corresponding variable value. So let's say if x1 is equal to 1, then the contribution is given by 5. x1 equal to 2, the contribution is 10, and so on. So it's proportional to the value of x1, and similarly the contribution of x2 is proportional to the value of x2 and is given by 3x2. Second, the additivity assumption is again a part of the definition of a linear function. Contributions of variables are independent. When I increase or decrease the value of x1 or the value of x2, it only impacts the corresponding term containing that variable and not other terms in the function definition. This again is a part of linearity assumption, and because everything is linear in linear programs, we cannot avoid both of these assumptions here. The third assumption is the divisibility assumption that tells us that the decision variables can take fractional values. This essentially says that we cannot require the variables to be integers, so fractional values satisfying all the constraints will be considered feasible solutions to our linear program. Some of the examples we considered before dealt with production of items whose quantities must be integer. In this case, of course, we cannot claim that the linear model is precise. In fact, it allows the fractional values for the items where it is physically impossible. For example, you cannot have 1/2 of a car or some other items that are countable. However, even in cases where we are dealing with inherently integer programs, their linear approximations can provide some useful information about the system that the model describes. Finally, the last assumption of linear programming listed here is the certainty assumption. According to this assumption, each parameter in the model is known with certainty, but it is well established that there are very few things in this world that are certain. So these four assumptions are always implicitly present in any linear programming model, and we have to recognize that whenever we use a linear programming model, you cannot really get rid of any of these assumptions. They're an integral part of this methodological framework. And of course, if you look back at all the examples that we considered so far, and I strongly recommend you to go back and analyze every single LP model we formulated so far and think about how reasonable each of these assumptions is for this model, then you'll notice that in most cases, at least one of these assumptions doesn't make much sense. Then you may argue, why should we even think about using this methodology if the underlying assumptions may not be true? But the same argument can actually be made about pretty much any methodological framework. The real world systems tend to be very difficult to describe precisely, and typically we have to resort to some kind of an approximation, and we have to balance between our ability to describe the model with a good level of approximation and our ability to solve the corresponding problem. So let's say if we drop some of these assumptions, then the model we may get may be extremely challenging, meaning that we cannot really solve them to optimality. So for example, if we drop the first two assumptions, then this would allow the functions involved in the model to be nonlinear, and we are in the realm of nonlinear optimization, which is extremely difficult. If we drop divisibility assumption, then we are talking about integer programming models, and these are also extremely difficult to solve. And finally, if you drop the certainty assumption, then we talk about stochastic optimization, which is again a class of problems which are extremely difficult to solve. I want to conclude this video with an optimistic statement by a famous statistician, George Box, who said that essentially all models are wrong, but some are useful. And linear programming is a methodological framework that can be claimed to be wrong in most cases, but in a very large number of cases it is extremely useful, and that's why it is a very, very popular framework used in pretty much any industry these days.
You have to let it all go, Neo. Fear, doubt, and disbelief.